In this video lecture we're going to look at network addressing and how it fits into the overall picture of a computer network system. We use a wide range of addresses in everyday life. These include phone numbers, street addresses, and map or GPS coordinates. So similar addressing schemes need to be employed when building a computer network to allow the data to get from one place to another and arrive safely at its destination. We can see in this diagram here that we have the TCP/IP or Internet model on the left-hand side and the type of addressing that occurs at each layer of that model on the right-hand side. So for example, at the network access layer at the bottom, we can see that we have MAC addresses. Remember that MAC address is a 48-bit addressing system that is attached to the network card or other device and is a physical address. In order to change a MAC address, you have to physically change the hardware of the device. Moving up to the next layer, we have an IP address. This is what we're going to focus on in this video lecture. This is a logical address. It's relatively easy to change just by re-entering some numbers into a piece of software. Likewise, as we go up through the model, we can see that there are other types of addressing used at other layers too. In a moment we'll look at why these different addresses are required at different layers. So if we take an analogy here of a postal letter, if we think about the type of structure we have in the address for a postal letter, we'll see how that links to the structure of the TCP/IP model and the different addresses at each layer. So we can see that we've now put alongside the different layers and the different addresses different components of a street address that tell us something different about where that particular house or building is located. Likewise, looking back at the addressing model we're using for TCP/IP, we can see that each of the different addresses at the different layers tells us something different about how to get the data to that particular device and that particular piece of software on that device. So now let's look at the example of how we get an email from a source network, such as the one at the bottom right, with an IP address of 12.128.9.3, to the computer on the left-hand side with the IP address 65.3.2.5. So once the email address has left the gateway, the router of the network that sourced it, that it came from, it enters the Internet cloud. At this stage, a decision needs to be made. As you can see in this simplified diagram, there are two different networks that it could possibly go to. In the real Internet, there could be thousands, hundreds of thousands of possible networks. So a decision needs to be made as to which is the correct network to send it to. Now, the data that is attached to the email includes the IP address of the destination network that it needs to get to. So by using that, the correct network can be identified using the IP address. We'll see exactly how this works later. We can now see that the correct network has been identified and it's heading towards the router, which is the gateway for the network that is the destination for this message. Now that we're on the correct network, we need to get the data to the correct computer. This is where the MAC address comes into play. Remember that the MAC address is a physical address built into the network card of the computer. Now the data that we have attached to the email has the IP address of the destination computer on it. However, the switch is not able to identify a computer via an IP address, only via a MAC address. So we use a protocol called ARP, Address Resolution Protocol, to convert the IP address to the MAC address. Once this is done, the data can be routed to the correct computer on the network via the switch. We've now successfully located the correct computer. However, we now need to ensure that once we're at the computer, we identify the correct type of software to handle this data, in this case an email. So we're now going to look in detail at what happens once it gets to the correct computer and passes up from the transport layer to the application layer of the TCP/IP model. Different network services running on a computer are identified via their port number. The port number is another logical address, so each network service has its own unique port number. We've just listed two of them here, port 80 for HTTP, the application layer protocol responsible for transferring web data, and port 25, SMTP, the port used for transferring email. So in this case, the port number is inspected and found to be port number 25 for email, and therefore it's passed to the correct piece of software for handling email. Now that the correct software has been identified, the email can be processed and delivered to the correct recipient as normal. So we've seen how there are different addresses at different layers doing different jobs. We used IP addresses to identify the network, and once we were at the network, we then used the MAC address to identify the computer. But why can't we just use the MAC address to identify the whole computer and the network in the first place? Surely this would make things simpler. The first problem with this is that MAC addresses do not have a geographical structure to them. While they do have a structure in the fact that the first part of a MAC address identifies the manufacturer of the network card or device, and the second part is a unique identifier for that particular device, these are not arranged geographically. This would be similar to having the idea of postcodes. If we used the similar sort of idea as a MAC address with a postcode, the postcodes would be arranged by the companies that deliver them, not necessarily by where the houses are located. This would make it very difficult to locate an individual house via the postcode. So, bringing this back to the idea of a MAC address, we cannot use a MAC address for routing data to the correct network, because MAC addresses are not organized geographically, they're organized by manufacturer. Because MAC addresses are physical, not logical addresses, this leads to our second problem. Even if we could structure MAC addresses in a geographical manner, we would have to buy new network cards to be able to create this structure, and we'd have to physically take hardware out of computers, swap them around, and put them into other computers as well to create this. This would be very time consuming and also would essentially lead to a lot of wasted money and equipment. The final problem is that the type of addressing used, MAC addressing, is only consistent for Ethernet technologies used in local area networks. If we used other types of technology to get the data from one place to another, as we commonly do on wide area networks, this means that the type of addressing used changes between technologies. This means we can't use a MAC address to get us from one end of a network to another. We have to use a different type of address. So hopefully we've now shown that you do need network addressing, and the standard used for network addressing are what we call IP addresses. There are two different types of IP address, version 4 and version 6. Version 4 is the type of address we commonly use nowadays on all of our networking technologies. This has been in use for quite some time and has a number of issues which we'll explore in a moment. We have a newer version as well, version 6, which is very, very slowly replacing IP version 4. However, although IP version 6 has a number of major advantages, it's not replacing IP version 4 at a very rapid rate. Some of the reasons for this are the fact that IP version 6 is very different to IP version 4. Support for IP version 6 is not universal. Windows Vista was the first version of Windows to ship with support for IP version 6. While it is possible to use IP version 6 on older versions of Windows, such as Windows XP, extra software needs to be installed to do this. Likewise, routers and other Internet and network devices require upgrades to be able to support IP version 6. Some of these are software upgrades, but in some cases the hardware itself will simply not support IP version 6, so needs completely replacing. This means upgrading to IP version 6 can be costly and time-consuming. So let's look a bit more at IP version 4 addressing. IP version 4 uses a 32-bit number to identify each device on the network. This is the IP address. This leads to just over 4.2 billion possible addresses. The IP address, though, is commonly written in decimal, split into 4 groups of 8 bits, or octets as we call them, separated by dots. Here we can see an example of an IP version 4 address, split into 4 groups, 4 octets, by dots. However, the fact that it is 32 bits long is very important to us, as we'll see later on. So the whole IP address is 32 bits, this means that each of the octets must each be 8 bits in length. Since each of the octets, which we label octet W, X, Y, and Z, is 8 bits in length, no number in decimal in the IP address can exceed 255, as this is the maximum permissible number for an 8-bit integer. Here we can see the same IP address written out in binary. Notice that we have the bit positions in yellow, the bit position values in red, and the IP address in binary in blue, with the dotted decimal form underneath. So now let's take a brief look at IP version 6, the successor to IP version 4 that is still not commonly used. We're not going to look at this in detail because it's not commonly used, but we are going to use it to identify some of the differences. One of the major problems with IP version 4 is there are only 4.2 billion addresses available. While this may sound an awful lot, remember there are 7 billion people in the world. Therefore, there aren't enough IP addresses for one IP address per person. Given that every device connected to a network requires an IP address, and people commonly now have multiple devices on them at any one time, this means that people require more than one IP address each. IP addresses must be unique, so we're clearly going to run out of these very, very quickly. Only because of the fact that not everybody is connected to the internet yet have we still got some available. We've also come up with clever ways of saving IP addresses as well, some of which we'll talk about in future lectures. However, IP version 6 solves this problem completely by having a vast amount more of IP addresses, 3.4 times 10 to the 38, by using a 128-bit number rather than 32 for the IP address. So, now that we have so many addresses available, we can create a structure in IP version 6 that is less complicated than the IP version 4 structure, which we'll come on to later. We can now just split it up into two parts. A network part, which is 64 bits, and a host part, for identifying the computer on that network, which is also 64 bits. We have so many IP addresses available that the wastage of potential networks or host parts because of this arbitrary split is not really a worry to us. Looking at what an IP version 6 address looks like, you'll see it looks an awful lot different to an IP version 4 address. The first things you'll notice is that it's actually now represented in hexadecimal, not decimal. And rather than being separated by dots, it's separated by colons. The other thing we notice is that because it's a 128-bit number, it's much, much longer, and therefore is much harder to remember and will also be much more complicated to correctly enter into a networking device without making a mistake. So in order to simplify this, where we have large groups of zeros, we can compress the zeros and omit them, as we've done in the example below. And in fact, when we have consecutive groups of zeros, we can omit them completely by just putting two colons in like this. However, the situation remains that IP version 6 addresses look much more complex than IP version 4 addresses. So in the previous slides we mentioned that there is a structure to IP version 4 addresses. We're now going to look into how that structure is created and why it's needed. As we can see from the examples of the telephone numbers at the top of this slide, there is an area code attached to every telephone number. This area code identifies the geographical region in which the telephone exists, allowing a telephone call to be quickly routed to the correct telephone exchange. The same is also true of networks, however the structure is not quite so obvious. An IP address is comprised of two parts, the network address and the host address. And the network address is essentially the equivalent of the telephone number's area code. It gets the data to the correct network. Once it's on that network, the correct computer can be identified. So in the examples here, we can see that we have the 0121 area code for the telephone numbers, and likewise we have the 129.102.0.0 network address, which identifies this particular network uniquely in the world. So here's an example. We have network A on the left-hand side, and the destination is network B. Each of the networks in between has IP addresses associated with it and therefore has a network address. Using this mesh of network addresses, we can route data from network A to network B. The devices represented by the blue circles with the arrows are routers. Remember that routers are network layer networking devices, and these use the IP address to obtain the network address. Once the network address is obtained, they can then send the data in the correct direction so that it ends up at their destination. So how do we identify the network address? Well, first of all, before we can do that, we need to look at some more structure relating to IP addressing. IP version 4 addresses are split up into classes. Now, these classes have been around for a very long time, but they are still utilized. We can see here in the diagram below that we have classes A, B, C, D, and E. For the purposes of what we're doing here, we're only going to consider class A, B, and C. It's very simple to identify what class an IP address is. You simply look at the number of the first octet highlighted here in red. If that number is between 1 and 127, it's a class A address. If that number is between 128 and 191, it's a class B address. And if that number is between 192 and 223, it's a class C address. Each of these IP address classes comes with a default subnet mask. Now, a subnet mask is another piece of networking information that is used to identify what part of the IP address is the network address and what part of the IP address is the host address. We'll see how we do this in a moment, but for the time being we're just going to look at the patterns that exist in the subnet masks relative to the class of IP address. You can see that for class A addresses the subnet mask is 255.0.0.0. For class B addresses the default subnet mask is 255.255.0.0, and for class C the default subnet mask has 3 lots of 255 with a 0 on the end. So what this allows us to do, as we'll see in a moment, is identify what part of the IP address is the area code, the network address, and what part is the host address, the telephone number. So we're now going to look at how we identify the network address and the host address from the IP address using the subnet mask. Now, the method I'm about to show you is a shortcut method. This method will only work where we are using the classes of IP address on the previous slide. We cannot use this method when we have created our non-default subnet mask, as we will do in more advanced topics. However, this method is quick and it's simple, and we'll look at a more detailed way of identifying this in a moment. So the reason why this is important is that all computers on the same network must have the same network address. If they do not have the same network address, they cannot directly communicate with each other. They must communicate via a correctly configured router. Therefore, if you have the correct network address, communication will occur. Incorrect network address, the computers won't be able to talk to each other. No two networks can have the same network ID. This would be the same as two areas such as London and Birmingham having the same area code. Calls would be incorrectly routed to both areas. So all networks have to have a different network ID. This has to be unique on a global level. And no two hosts on the same network can have the same host address. This would be like two telephones with the same telephone number. So how do we know what part of the IP address is the network address and what part is the host address? Well, with a telephone number it's quite simple, as there is a defined structure to it. Generally the first 4 digits define the area code and the remainder is the telephone number. This is slightly more complex when we come to IP addresses. With an IP address, the subnet mask defines which part of the IP address is the network portion and which the host portion. We can see this in the example here. When we're using a default subnet mask, where each of the octets in the subnet mask is a value of either 0 or 255, we can use the simple method illustrated here to identify the network address. Where a 255 appears in the subnet mask, the corresponding part of the IP address forms part of the network address. So here we can see on the left-hand side the 192 forms part of the network address because the corresponding part of the subnet mask is 255. Moving along to the second octet, we can see that the 168 forms part of the network address because there is a corresponding 255 in the subnet mask. Likewise, the 1 forms part of the network address because there is a corresponding 255 in the subnet mask. However, in the final octet, the final one does not form part of the network address because there is a 0 in the subnet mask. So the final network address is 192.168.1.0. So let's have a look at this now for two examples. The first example, 10.15.3.1. This is a class A IP address because the first octet has a value of 10, which is between 1 and 127, making it class A. This means the default subnet mask is 255.0.0.0. Using the method from the previous slide, wherever there is a 255 in the subnet mask, that part of the IP address forms part of the network address. We can see the network address would be 10.0.0.0, as only the first octet of the subnet mask has a 255 in it. Whatever remains of the IP address, once we've subtracted the network portion, forms the host ID. So here, 0.15.3.1. We can see that this corresponds to the zeros in the subnet mask. In the next example, 153.212.6.5, 153 is between 128 and 191, so making this a class B address. That means we have a subnet mask of 255.255.0.0 by default. So again, using the same method, we can see that because the first two octets of the subnet mask contain 255, we look for the network address at the first two octets of the IP address. So the network address will be 153.212.0.0. This leaves the remaining part of the IP address, the 6.5, to form the host ID, as we can see here. Now, as we said earlier, this is useful when we have simple classful addresses that utilize the default subnet mask. As we'll find out later on, this is not quite so simple in real life. Sometimes we don't use the default class boundaries and the default subnet masks. And we'll look at a method now that allows us to identify the network address even when we don't use the default values. So the method we're going to look at now is the method that underlies the shortcut method we've used on the previous slides. However, this method can be used not just for the classful address boundaries for default subnet masks as we've seen, but also for any subnet masks for when we do subnetting, which is a topic we'll come on to later on. This method means that we need to write out the IP address and the subnet mask in binary, one above the other, and then use a logical AND function to work out which parts form the network address and which the host address. So here in the example in the table below, you can see that we have written out the same IP address, 192.168.1.1, in the white row in binary. We've then taken the default subnet mask for class C, this is a class C address, of 255.255.255.0, and written that in the green row. What we're now going to do is use the logical AND function to work out what the network address is. So remember, with an AND function, two ones need to enter the AND function for the result to be 1. If any of the inputs are 0, the result will likewise be 0. So if we start at the left-hand side and look at the green row for the subnet mask, we'll see that the first bit, representing 128, of the subnet mask is a 1, and the corresponding bit beneath that in the white row for the IP address is also 1. This means the result of the AND function, which will form the network address, is also 1. If we look at bit position 2, we find that we also have two 1s, one in the green row, one in the white row, the result being 1. However, for bit position 3, we find that we now have a 1 in the subnet mask but a 0 in the IP address. This means the result will be 0. If we follow this across all the way for the full 32 bits, we find that the resulting network address that we end up with is identical to the simple method we used earlier, which is what we would expect. However, this method works when we're working with complex, non-standard, non-default subnet masks, as we will when we're dealing with subnetted addresses, which we'll talk about in a future lecture. So, to establish whether two IP addresses are on the same network or not, we need to do the following. Convert both IP addresses to binary, along with their subnet masks. As we did previously, and both addresses with their corresponding subnet masks to create the network address. If the results of this are the same, i.e. the network addresses work out the same, they're on the same network, allowing the computers to communicate directly without the aid of a router. If they're not the same, then they will need the aid of a router to communicate. This means that it will have to be configured to communicate via a default gateway, which must also be configured. Let's run through an example of this. Here we have two IP addresses, 192.168.123.45 and 192.168.123.57. The question is, are they on the same network? We're now using a non-default subnet mask. Notice it's no longer the default 255.255.255.0 subnet mask. The final octet has now been changed to 224. How this occurs we'll talk about in a future lecture when we talk about subnetting. For the time being, let's just assume that this information is correct. So let's convert the first IP address into binary, as we've done here, and then do the same with the subnet mask, as we've done here. Notice this time with the final octet it's 224, so it's not all zeros this time. We have 3 ones appearing in the final octet of the subnet mask. We now need to AND the IP address with the subnet mask, as we did in the previous example. Again, we're looking for both ones in the IP address and the subnet mask, which will produce a 1 in the result, and if there's a 0 anywhere, that will produce a 0. So this is the result we get from ANDing those two numbers together. If we now convert that binary number back into a dotted decimal format, we find we have a 192.168.123.32 network address. We now need to repeat the process for the second IP address, 192.168.123.57, using the same subnet mask in this case. Again, we convert the subnet mask into binary and AND the two numbers together. We produce a result and convert that into dotted decimal format and then compare the two results. And in this case we find that both network addresses are the same, so these two computers can communicate directly without the aid of a router. So, let's summarize what we've covered in this video lecture on network addressing. We firstly looked at the 4 layers of the TCP/IP model and which addresses appear at which layer. So for example, starting off at the bottom, we start off with the network access layer where we have the MAC address, the 48-bit number that's usually written in hexadecimal. Remember, this is a physical address built into the hardware, and the problems with this is it has no geographical structure to it. Moving up to the internetwork layer, we now have the IP address. The IP address is a logical address. For IP version 4, this is what we looked at in detail, this is used for routing data between networks. Moving up to the transport layer, we have the port numbers. The port numbers are used for identifying which application layer protocol the data needs to be sent to. And finally we have the application layer. At the application layer we have protocol numbers. Once we'd outlined the different addresses that are available at each layer, we then summarized how these are used to allow end-to-end data communication across a wide area network. Once we understood the need for network addressing in this picture of data communications, we looked at briefly the differences between IP version 4 and IP version 6 and summarized why IP version 4 is still commonly used, even though it has a number of disadvantages over IP version 6. We then looked at some of the properties of an IP version 4 address, before moving on to look at the structure of an IP version 4 address and how the network portion and the host portion can be identified by means of the subnet mask. We then looked at classes A, B, C, D and E of IP address, focusing in more detail on classes A, B and C. Remember, for class A addresses, the first octet must be between 1 and 127, and this would give a default subnet mask of 255.0.0.0. For class B addresses, the first octet is between 128 and 191, and this has a default subnet mask of 255.255.0.0. For class C, we have a first octet between 192 and 223, and a default subnet mask of 255.255.255.0. We then finally looked at how we could use the subnet mask with the IP address to work out the network address and the host address.